Welcome back everybody to our course on memory device technology for AI/ML computing. So today we are going to wrap up this module where we had looked at neuromorphic computing and the hardware implementation of neurons. Today we will look at hardware implementation of synapses. But before that, let's have a quick recap of what we studied the last time around, which was primarily synaptic plasticity. So we saw how signal transduction is affected by the synapse. So when the neuron fires an action potential, the spike travels down the axon and reaches the synapse, the junction where neurons communicate. It is here that the signal can be strengthened and weakened and even blocked. So while neurons generate these spikes, it's the synapse which decides the strength of these connections and thereby making possible all this adaptability in form of learning and memory. We also discussed in detail what is synaptic plasticity, which is the ability of tuning the weight of the synapses depending on the firing of the pre and post synaptic neuron. Remember, we called this as the local learning rule. Local learning rule basically means that the synaptic weight update simply depends on the firing of the pre and post synaptic neuron, not on some global objective function, just is as the case in artificial neural networks. And this is what can make spiking neural networks, which use these local learning rules, very powerful, because you do not need to have these very energy expensive backpropagation algorithms. Also, we discussed the different timescales over synaptic plasticity manifesting. It was the short-term plasticity, which causes fast reversible changes during continuous activity of the presynaptic neuron. And we had seen how to measure short-term plasticity in form of pulse bed facilitation. And also we looked at long-term plasticity, and one of the important learning rules such as spike timing dependent plasticity, which was discovered quite recently in the late 90s. As you can see in this diagram, in STDP, the synaptic weight depends on whether there is a correlated or uncorrelated firing between the pre and post synaptic neuron. If the post synaptic neuron fires after the presynaptic neuron, there is a potentiation. And if the opposite is the case, which is uncorrelated firing, there is depression. Okay. So today we are going to end this module by looking at the hardware implementation of synapses, starting with traditional CMOS based approaches and moving towards emerging non-volatile memory or ENVM designs. But before we do that, it's very important to appreciate a very important concept, that the way synapses are realized in the two key neural network paradigms is fundamentally different. So the two key neural network paradigms are artificial neural networks and spiking neural networks. And although we have in detail looked at ANNs in the previous module and are going to look at SNNs in the next module, this section will only make sense if we have a little bit of understanding of what are the varying requirements for synapses when they are implemented for ANNs and SNNs. So as you can see on the left, in ANNs, each input X is multiplied by the weight W and summed up and passed through a continuous activation functions. Here both the input and the output are continuous values, and the computation happens primarily in the spatial domain. So the synaptic weights are scalars at the level of one ANN layer that simply scale the amplitude of these input signals. Now, if you contrast this with what we will be seeing next, which is spiking neural networks, here the inputs and the outputs are both spikes. They are basically binary events. Either they are there or they are not there. They are binary events in time. And what the neuron does is it integrates these spikes, and when the membrane potential hits a particular threshold, it emits an output spike. So unlike ANNs, SNNs work in the spatio-temporal domain, where both space and time matter. So these synaptic weights here, which are modulated, are not continuous signals, but they are based on discrete spiking events depending on whether the pre or post synaptic neuron is firing or not. And also, as we saw, it depends on the interspike interval between the pre and post synaptic neuron. And since in ANNs and SNNs, the synaptic learning and weight update mechanism are entirely different, the implementations of synaptic weight also is entirely different, and that is what we are trying to focus on. So as you see on the left hand side, we have a synapse for a artificial neural network. So here the weights are actually controlled and governed by a global supervisor. What is a global supervisor? It is the algorithm or the hardware which is running your backpropagation algorithm. What it does, it knows the current weight, and depending on how the current weight affects the global cost function, the new weight is computed. I hope you remember this from our study. Here, the updates to our weight depends on the global cost minimization. And once the new weight is decided, it tells a pulse generator that you give appropriate pulses. Either you give positive pulses or negative pulses, so that the synaptic weight, which is generally modeled in hardware as a linear tunable resistor, can be modulated. For example, if you have to increase the weight of this particular synapse, you possibly give positive pulses, and after each positive pulses, you can see there is a update, as you can see from these dots in the conductivity of the device, and that is called potentiation because it is increasing. Or if you want to reduce the weight, you can apply negative pulses and there will be a depression. So this is in essence what you would want from an ideal synapse, which is built from an individual hardware element, which will be then implemented in artificial neural networks. However, the implementation for synapses for spiking neural networks will be entirely different. This is because there is no global supervisor. Instead, learning is happening just looking at what is the difference in spiking between the pre and post synaptic neuron. So this is what we saw in essence was the spike timing dependent plasticity behavior. Here the amount of weight changes depends exponentially on the spiking time difference. So while ANN synapses rely on global error driven learning, SNN synapses rely primarily on local timing dependent adaptations. So in SNNs, the synapse just needs to be a STDP based resistor where the conductance of the device, which is a representation of the synaptic weight, will change just depending on the firing of the pre and post synaptic neurons. So with this knowledge, whenever you fabricate or measure a device or even see one that is reported in literature, you should immediately be able to tell whether the device is well suited for ANN type of learning or for SNN type of learning. So let us go through each of the characteristics in the table, contrast both of them directly so that we have a very clear idea. So the first thing that we will look at is the weight precision and linearity. For ANN synapses, as you can see from this image, you would require very high precision and the ability to tune these weights in a very highly symmetric and linear manner. This is because the gradient descent relies on accurate numerical adjustments. It has been shown in several studies that this linearity in weight updates and the symmetricity in weight updates really affects the performance of the overall network to classify problems. If the linearity becomes little bad, the classification accuracy also suffers. If you contrast this with the synapses required for SNNs, they can actually tolerate a lot of variability. This is because biological learning and biological systems are generally much more robust to noise. However, they must support temporal dynamics, that is, the ability to evolve based on spike timing rather than spike amplitude. The next is plasticity and adaptivity. As we just discussed, while AN and synapse need to be completely deterministic and their weight changes have to be very, very stable. Once they are set, they need to be very constant. They don't need to change they should not change with time. In case of SNN synapses, that is not a very mandatory thing. All it needs to do is it needs to support these local learning rules such as STDP. If we look at stability versus variability, we see that although ANN synapses need to be very, very stable with low noise, for reasons that we have just discussed, SNN synapses often, as we will see at the end of our lecture today, sometimes even benefits from a little bit of stochasticity in the weights. And this helps the system not get into some local minimas and allows for the complete exploration of the parameter space. Finally, we will discuss about latency and timing sensitivity. ANN synapses are generally running at much faster rates, so a low latency is highly desirable, but SNN synapses, even a microsecond level timing is okay. This is because synapses in SNN will basically mimic event-based computing. So in event-based computing, it is not often that one synapse is active all the time. It is just based on the events. So this relaxes some of the considerations on how frequently these synapses are getting updated and also how quickly they need to be updated. So let us now begin our discussion. First, we will look at the digital implementation of synapses using traditional memory technologies such as SRAM, DRAM, and flash. These form the backbone of what we nowadays refer to hardware for AI 1.0. These are your classical deep learning era. In these systems, as you can see, the synaptic weights are not these physical devices or conductance states. They are simple integer or numeric values, or actually bits, which are stored in your various forms of memory. So on your left hand side, you can see a typical ANN system. This is also a proxy for what we see in GPUs nowadays. So in such systems, the learning process is fully digital based on global updation of weights depending on the global cost function. And these weights are treated as static data that the processor keeps modifying. And this is a very classical von Neumann architecture where computation and memory remain separate. However, this concept can also be used to implement spiking neural networks, and that is what has been done by IBM's True North. Here also you see that these SRAM array within each core is what constitute of the weights. But here all the learning happens off chip, and once it is trained, the weights are simply uploaded to the SRAM, which is always stays inside the True North system. During the operation, only spiking activity is dynamic. The weights remain fixed, serving as a lookup values that determine how the spikes are routed and how they are scaled. In newer digital implementations that we will see later in our course, such as Loihi, on-chip learning is possible, but it is still handled by some external supervisory logic or control circuit. What I mean is that the weight update is happening based on spike timing dependent plasticity, but this decision is not made by that nanoscale element or the synapse. It is made by some other digital logic. So while both these implementations of ANNs and SNNs in digital logic using traditional memories are very promising, of course they suffer from the same problem of the von Neumann bottleneck. And since synaptic weights are stored separately from the computation units, every weight update requires constant data movement, which leads to really high power consumption. Also, there is a big area overhead with very, very limited scalability. This separation also means that weight updates are handled externally, as we discussed, by some other digital control logic, preventing true local or adaptive learning. And to address these issues of rising power consumption and area, even in these digital implementations of ANNs and SNNs, two key strategies are to be used. So today we will discuss the first strategy, which is converting entire digital weights into analog weights. In this strategy, analog or multi-level devices, a single nanoscale element which can show multi-level conductance, are used, which can represent the weights, enabling local and continuous learning, and that is what we will focus on today's lecture. The second approach is to bring this compute and memory as closely coupled as possible, and this is the new strategy of in-memory computing. And the key idea here in in-memory computing is to do the computation within the memory itself, thereby minimizing the data movement. And that is what we will study in detail in the next module. So let us now begin by exploring analog synapses, the devices that can store and gradually tune multiple weight levels in form of conductance states. One of the most established approaches comes from floating gate transistors, the same floating gate transistors that is used in flash memory, which can trap charge based on an isolated gate and retain it for several years. Often Carver-Mead's name comes up when we discuss about neuromorphic computing, and he was the first person to build this silicon retina, as we have discussed at the beginning lecture of this particular module. But very few people know that his group was amongst the first to demonstrate that an analog synapse can be built directly using floating gate transistors. And really, he was a very visionary person, I would say, because he not only showed that for a single device, he also integrated these devices into arrays to show that the cross interference when you operate one of the synapse is not significant. So that is what he has shown here. You see the synapse at 1, 2 and 2, 1 are really silent, whereas all the weight updates is happening from the 1, 1 synapse only, which is being targeted. Next, let's discuss how is the floating gate transistor showing us synaptic behavior. How is there a increase and decrease in the synaptic strength? So what essentially happens is that the floating gate transistor here has two key operations. It has the injection operation, where the electrons are added to the gate, which causes depression. Why does it cause depression? Because the threshold voltage of the transistor shifts on the right hand side in an NMOS transistor, whereas tunneling process causes potentiation, where electrons are removed, thereby causing the synaptic weight to increase, which is also known as potentiation. A very important thing to note, the lower plot also shows that the resulting weight evolution, change of synaptic current, changes non-linearly with programming steps, and it follows an exponential relationship rather than an ideal linear update which we expect. This happens because charge trapping and detrapping process in a floating gate transistor are inherently exponential physical processes. More importantly, Carver-Mead's work also shows low cross interference between adjacent synapses, meaning individual weights could be tuned precisely without disturbing the neighboring ones, which is a very crucial thing for large-scale analog arrays. Next, we shall see how spike timing dependent plasticity is implemented in floating gate synapses. But it is very important to understand at this juncture that a direct application of pre and post synaptic spikes does not really work in most solid state devices. This is because any solid state devices, especially in this case a floating gate transistor, doesn't inherently understand timing or causality. It only responds to the voltages applied across the terminals. So to make it behave like a biological synapse, we need to somehow encode timing information into voltage pulses, and this process is known as pulse shaping. So as you can see in the circuit shown over here, when a presynaptic spike occurs, a gate waveform is generated, and when a postsynaptic spike arrives, a drain pulse is produced. The degree of overlap between these two pulses determines what happens inside the floating gate of this particular transistor. If the pre-spike arrives before the post-spike, the overlapping waveforms create an electric field which is strong enough to trigger electron injection into the floating gate. And this adds charges and leads to a long-term potentiation, as shown on the right hand side of this STDP plot. If the postsynaptic spike arrives first, the overlap produces a condition which favors tunneling. Therefore, it removes charges from the floating gate, causing a long-term depression as seen on the left-hand side of this STDP curve. But this is a bit contradictory from what we studied just now regarding this work. Here, the injection was causing a depression and tunneling was causing potentiation. Why is it opposite in this particular case? This is because, please note very carefully, the floating gate transistor that we are using here is not NMOS but PMOS. So as you inject more electrons into the floating gate, it leads to the threshold voltage moving on the right hand side, and therefore there is increased current. Because you are changing the polarity from NMOS to PMOS, even potentiation and depression trends are flipping. So to conclude, this classic STDP window that you see over here is not really an intrinsic property of the device. It is entirely a result of carefully shaped pulses, both in pre and post timing circuitry. And this same principle, using external waveforms to mimic timing dependent plasticity, is what we will see in other emerging non-volatile synapses as well. And this is the main promise of ENVN based synapses. While your floating gate transistors can show both close to linear weight updates and STDP, the promise of ENVMs is better area and power scalability, and of course much lower latency. So let us move ahead and look at the first commercially mature class of emerging ENVMs, which is your phase change RAMs or PC RAMs. Please try to recall, when the material inside the PC RAM is in fully set state, it is crystalline and therefore it has low resistance. When in reset state, it is amorphous and highly resistive. And therefore, by finely tuning the magnitude and duration of the programming pulses, we can create several intermediary partially crystallized states, each corresponding to a unique conductance level. And this ability to achieve multiple stable conductance states is what initially made PC RAMs excellent candidates for analog synaptic weights. Now, in the context of ANN type learning, these states are typically programmed using non-linear pulses. Ideally, you would want the same identical pulses to create potentiation and depression, but as you can see, because the behavior of partial crystallization and recrystallization is also non-linear, in order to get reasonable weight updates, you need to have non-linear pulsing. A good example that I give in class is, suppose you want to fill air in the balloon such that after each blow, the balloon expands uniformly. Now, as you know, once you first blow the balloon, it is much easier to fill more air into it. and consequent increase in volume of the balloon require much more effort. So if you have to flip the problem around and make sure that amount of volume which goes into the balloon each time is the same, you need to change by how much force you are pumping the air each and every time. And this is the very simple philosophy which is also used in ENVM synapses to get near linear weight updates. Next, let's move to seeing how PCRAMs are implemented in facilitating spike time dependent plasticity. And here again, the device has no intrinsic sense of time and the learning behavior is induced through pulse shaping. As you can see in the top two panels on the right hand side, the pre and post synaptic spikes are converted into continuous voltage waveforms that overlap differently depending on what is their timing difference. If the pre-spike arrives before the post-spike, as you can see over here, the net result is that the overlap creates a heating and crystallization which corresponds to potentiation, as you can see over here. And if the post-spike comes first, the opposite overlap creates a depression which is triggered by having the device go into amorphization. And this is what is shown in the bottom plots with the measured STDP curves with a characteristic exponential timing window in both LTP and LTD. To conclude our discussion about PCRAMs, it is safe to say whether it is to be used for ANNs or SNNs, PCRAMs are such nonlinear devices that most of their work is being facilitated through pulse engineering. And that really adds a little bit of more complexity in the external peripheral circuitry. So next we will move to RRAMs. And I would admit that amongst all the emerging NVM technologies, my belief is that RRAMs are inherently the most versatile and promising candidates for analog synapse implementations, as you will see when we study our last module. And this is because they have excellent CMOS compatibility, low power operation, and as we will see in this slide, there is this tremendous ability to engineer both the materials and the pulsing schemes to achieve the desired analog weight behavior. So let us first start with conductive bridge RAMs or CB RAMs, as you can see on the left hand side. So this is one of the earliest reports of embedding silver in silicon based conductive bridge RAMs, where by applying positive and negative voltage pulses, metal ions migrate and form, or they can rupture these nanoscale filaments, leading to very gradual resistance changes. And as you can see in this plot, by controlling the pulsing behavior of these devices, the current evolves through a progressive potentiation, which is shown in blue color, or depression, which is shown in red color. However, what is most important is that this kind of ion migration behavior can be made very smooth and analog through materials engineering, as has been shown in this particular work, where by carefully tuning the ion mobility and oxide defect density, we can suppress abrupt switching and achieve more linear behavior in the incremental weight updates. So in this particular work, this was achieved by adding some titanium inside the silicon material, and that plays with the oxide defect density, thereby changing the ion dynamics inside this solid electrolyte. Now, next we will move to valence change RAMs or VC RAMs, which operate on slightly a different principle. Here, instead of ion motion, the resistance changes, please try to recall, is governed by oxygen vacancy migration within metal oxides like HFO2 or TiO2. And as has been shown in this very recent work, by tuning this functional layer instead of having one bulk HFO2 or Al2O3, if you make a superlattice is nothing but alternating deposited oxides, as you can see in this particular image, you can change the binary switching or abrupt switching behavior into more gradual analog switching. Furthermore, the lowermost panel shows how using pulse engineering you can further refine the behavior of VCRAM synapses. As you can see, if you apply identical pulses, there is a large bit of non-linearity, as you can see from these orange curves in the potentiation and depression behavior, which can be easily mitigated by doing some intelligent pulse shaping of using non-identical pulses, which can help in getting near linear behavior, as you can see in these magenta curves in both potentiation and in depression. Next, we will move on to study how both CB-RAMs and VC-RAMs can realize STDP learning, again through pulse shaping techniques. Let's begin with CB-RAMs, where again the same stack of silver doped silicon is used, and to translate this into synaptic plasticity, the pre and post synaptic spikes are shown in the middle such that their temporal overlap determines the net voltage across the synapse. So as you can see, when the pre-spike precedes the post-spike, the overlap produces a small positive bias as indicated by red color, which allows the filament to grow a little bit, thus mimicking long-term potentiation. When the order is reversed, the combined pulse polarity leads to a negative voltage across the synapse, and this encourages the dissolution of the filament, therefore leading to long-term depression, and that is evident in the STDP behavior of this device when subjected to this kind of pulsing scheme. Next, we will look at VCRAM based devices such as HFO2, where spike timing dependent plasticity was demonstrated in bipolar 1T1R HFO2 RRAM devices. Here, pulse shaping filters create asymmetric pre and post spike waveforms. If the spikes overlap in the proper polarity, such as delta T greater than 0, the combined potential leads to an increasing in the set threshold, therefore leading to an increase in the synaptic weight or the conductance of the device. Whereas if the overlap is reversed, the effective bias across the synapse happens to cross the reset threshold, giving it long-term depression. So both in CB-RAMs and VC-RAMs, as we have discussed even for PC-RAMs, the device does not really understand timing. It is intelligent pulse shaping circuitry that converts this spike timing into controlled analog state updates, thereby enabling spike timing dependent plasticity in actual hardware with a single nanoscale element. So to conclude our section on hardware realization of synapses, let me introduce a very interesting technique of making analog synapses through stochastic behavior of MRAMs. Now remember, the switching in MRAMs from anti-parallel to parallel to anti-parallel state is generally binary in nature. It is very difficult to have something between anti-parallel and parallel. However, this binary switching is not always deterministic. In fact, it is stochastic, as has been shown in this particular graph. You can see that there is a particular switching probability depending on the duration of the pulse. Why does this stochasticity happen? This stochasticity happens because there are competing effects between the STT current, which is trying to flip the device from parallel to anti-parallel state, and the existing thermal noise. When the barrier lowering due to the STT current becomes comparable to thermal noise, this results in a probabilistic switching. And it was realized that this probabilistic switching in binary elements can be used to facilitate analog representation of weights. This is possible by averaging out this probability over several cycles or devices. And this is what is indicated in this particular graph. The idea is very simple. Suppose I want a synaptic weight with a weight of 0.6 normalized to 1. So what I will do is I will bias my STT MRAM with these particular parameters of voltage and delta t duration. Then I will operate the MRAM at least 10 times. So the idea is 6 out of 10 times, because the probability of switching is 0.6, the MRAM will switch from 0 to 1. But the other 4 times the MRAM will remain in the 0 state. So on an average, we can represent the switching probability as a proxy for the weight. And this is how averaging of the probability over different cycles or different devices has enabled the representation into analog weights, both for ANNs and for SNNs. And initially, all this work was only limited to theoretical predictions. But very interestingly, in this year itself, there has been an experimental demonstration of such stochastic spike time dependent plasticity computation on very small 4x2 stochastic arrays from both Everspin and UT Dallas. Here, the probabilistic switching of MTJs is used to implement local Hebbian learning. When the pre and post synaptic occur in the right order, the potentiation increases the likelihood of switching to the parallel state, and when they arrive in reverse, the depression pulses encourage switching back from anti-parallel, switching back to anti-parallel state. And by encoding the probabilities into synaptic weights by averaging, you are able to essentially do computation. Okay, so with this, let us conclude our study of neuromorphic computing, the understanding of LIF neurons and their hardware implementation, and synaptic rules of plasticity and their hardware implementation. With this, we conclude our module, and in the next module, which is our final and concluding module, we will look at how all of these concepts are brought together to do very efficient neuromorphic computing in spiking neural networks and also using in-memory computing. Thank you very much for your attention. See you in the next class.